Again, welcome to our CTBUH Future Leaders Committee Chicago presentation about Wasl Plaza. Our speakers today will be Tim Winstanley, a senior architect with Adrian Smith Gordon Gill Architecture, and JJ Tobolski, an associate from Thornton Tomasetti Structural Engineering. My name is Katrina Fernandez Nova, and I am a senior architect at Adrian Smith Gordon Gill Architecture as well. And I am part of the Future Leaders Committee. Just so everybody knows, the program is being recorded. Everybody's mics are muted, but we will have some time for a Q&A session after the presentation. We won't be using the chat, so please make sure that for your questions, you use the Q&A button at the bottom of the screen. For those of you that aren't familiar, the CTBUH, or Council on Tall Buildings and Urban Habitat, was founded in 1969, and it's a nonprofit, multidisciplinary, worldwide association focused on tall buildings and sustainable cities. As of 2020, the CTBUH organizational member network included over 2 million individuals in over 10,000 offices around the world. The Future Leaders Committee, everywhere, but especially here in Chicago, we're a group of volunteers, we're young leaders in the industry, and our goal is basically to get future young leaders interacting, networking, and provide events such as these to give everybody an insight of what we're up to. Now I'm going to introduce our speakers. JJ Tobolski is an associate at Thornton Tomasetti's Chicago office. He has 10 years of experience as a structural engineer. A Chicago native, JJ has been involved in the design of numerous high-rise and cultural projects, both domestically and internationally, in addition to acting as one of TT's leaders in structural optimization. Tim Winstanley is a senior architect at ASGG, working across a range of typologies, including cultural, super tall towers, large-scale mixed-use developments that include 2 World Expos, including Dubai 2020+1, which we'll be presenting today. Tim leads some of the most complex design efforts at ASGG, which, along his on-site construction experience, ensures the design vision is executed correctly. That's it for my intro. I'm going to pass it on to our presenters. Take it away.
Thank you, Katrina. So today we're going to give a talk on the construction process that happened over the course of a couple of years for the Wasl Plaza in Dubai, the United Arab Emirates. And so just a brief overview of the project team. Our client was Expo 2020. The construction manager was CH2M Mace. The design architects were ourselves, Adrian Smith and Gordon Gill Architecture. Mechanical engineers was Hor Lee out of the UK. Our structural engineer, Thornton Tomasetti, and JJ is representing them here today. And the primary contractor for the trellis was Chimolai Rimond Middle East. So just a quick overview of the agenda today. We'll give a brief overview of the design, and then we'll move right into the steel fabrication and some of the structural implications. And then we'll move towards the steel erection that took place over the course of about 1.5 years in Dubai. And then we'll touch on some of the finer elements that include the fabric and portions of the immersive experience. So just a quick intro on the design. Just for everybody's background, World Expo is an event where countries from all around the world gather to present and showcase innovations that are happening in their country. And throughout the past 100 or so years, there's been numerous icons that have been known to represent those particular cities. So for example, in Paris, there's the Eiffel Tower. And then as we move along in the years, coming towards 2020, which is a very important expo because it's the first expo that's being held in the Middle East. And so the goal is to create a cultural icon for Dubai, and it's linking their main theme, which is connecting minds and creating the future. And so Wasl in Arabic means connection. And one of the main things that is behind the design of this is how to design an experience first, a place for connection and meeting. And so something that we've always been doing is exploring ways to enhance architecture and experience through immersion using on materials such as light, shadow, video projection, in addition to the solid built materials. So just so everybody gets their bearings on where this is located, I'm sure everybody knows where Burj Khalifa is in downtown Dubai. So at the very south end of the city, there's a new development called Dubai South, which is where Expo 2020 is going to be located. And the Wasl Trellis is the centerpiece of Expo 2020. So the image to the right is showing an under construction in the very early stages of what look like 3 petals, which will house thematic districts. And then around those petals are country pavilions with all the pathways leading back towards Al Wasl, which is the centerpiece of the whole development. So again, just touching on the idea of creating experience first, and how do we start to harness all the activity that is going on. So you'll see that the 3 petals, and there's pathways that encircle each one, everything leads back towards Al Wasl. And so this is seen as the heartbeat of Expo and will become a beacon for the Expo, and then lives on in legacy mode when the development transitions to a new neighborhood in Dubai South. So briefly touching on some of our design iterations, in the top left, you'll see something which is a hexagonal grid that is very straightforward and structurally efficient. And through the iterative process and design sketches, we transitioned towards something that was abstracted from the Expo logo, which is inspired by an ancient ring that they found in the desert. So ultimately, we took something that was very culturally significant and abstracted that into the filigree that became the steel structure for the trellis. And so one of the main things that we're going to talk about is how this was constructed, and one of the ways to construct something of this scale and magnitude. While from the outside it may look complex, it's actually simplified into 27 radial segments. And so this is a good segue into the fabrication because it leads to efficiencies during the fabrication process. And just to get an idea of the scale, the trellis is 130 meters in diameter. It's just under 70 meters tall to the top of the oculus. And the arc that makes up the frame of this is a 55-meter diameter arc. So again, touching on the simplicity of it, when you break it down, the image on the left is showing the typical section, which is the tall pie shape there. And then there are some atypical sections that relate to the United Arab Emirates Pavilion, which is the piece on the left, and then larger gateways that allow vehicular access into the trellis. And then as we move to the middle image here, what you see on the outside isn't necessarily indicative of all the activity that's actually happening within the pipe. So for the immersive experience, for maintenance, there's all sorts of conduits and utilities that are hidden within the steel tubes. And then the image on the right is showing the infill fabric panels. So there's several types of fabric panels that start to offset the steel. And just another quick image here for scale, showing the trellis in relation to the Pantheon in Rome and the Florence Cathedral. So just to get an idea of the scale. So this image here is showing what the Al Wasl Plaza and Trellis will look like during Expo mode. So the 6 months that Expo is operating, there's a bit more hardscape, but this is because it is going to be heavily occupied with all the visitors and there'll be events happening every night and during the day throughout the course of Expo. Now, the interesting thing is for the expos is typically expos are built and then they're deconstructed, but part of our vision at ASGG is to breathe life into these projects after the expo is done. So in legacy mode, once Expo wraps up, this becomes a garden and the central hub and node for the new development of Dubai South. So this will live on in Expo mode as a cultural anchor in the south of Dubai. And then touching on the aspect of the fabric and the steel and this idea of playing with immateriality. So playing with light and shadow and harder elements versus softer elements. So the fabric is an integral part of this project, not only because it diffuses the sunlight, but also because it becomes the canvas for the immersive experience. And just a quick stat rundown of some of the immersive aspect of it. Embedded within the steel pipes, there's roughly 2,800 LED lights that run along with the projectors. There's 42 projector enclosures that are cantilevered off the steel trellis, and then there's also 12 speaker enclosures that house these state-of-the-art speakers. And this is just a snapshot, which we'll touch on a bit later, but this is showing the custom projector enclosures on the top portion of the image. And then in the lower right, you can see what's still under construction are the speaker enclosures. And then this is a fairly recent picture. This is a projection all in red. This is indicative of the UAE's satellite just reaching Mars. So just to get an idea of the scale and the context of what's going on. The same thing here. This is an image actually. We'll go to the video. That's fine. We can start the video. So this is just showing some of the LEDs are going off there. This is during a test that we ran back in January, and showing the video projection in action here. And you can see the people at the bottom there for scale.
All right. Well, thank you, Tim. I think we'll catch back up with you when we start to get in the erection phase for when you were stationed over on site. So I'll just add in a couple more things about the structural design here, and I'll try not to be too dry and touch up on some of the important aspects of doing the structure of something so unique and interesting. So just to give you a snapshot of the different parts and pieces that we have here, the trellis itself does not sit directly on the soil. There is actually a central basement that is underneath all the plaza work, and there's also some site tunneling that is there to service the buildings around. So there was quite a few things that we had to contend with. So we actually have the framework sit, and it's founded on a concrete frame below it. And so this frame is simply composed of a concrete ring at the base, and then just a series of piers where each of the different arches come down of the trellis, and then a strip footing. There's no deep foundations here. There's actually some pretty good quality rock that we're able to bear directly on. And one of the things I just want to layer in and add is, you know, there was many different iterations. They were looking at very different frameworks early on, but there was also a lot of thought and attention paid to how these rings interface together. You know, in addition to having everything be simplified as a series of different pies along the circle, we also wanted to ensure that everything was planar and in a 2D curve so that it could also be fabricated in a reasonable manner. Not to say that's impossible to do some of those 3D swoops, but we knew that because of all the different complexities that we had on this project, if we could come up and really refine the geometry to a point that everything was 2D based, we'd have a good look. And it also had two things that it accomplished: not only just the fabrication, but it also helped achieve this really nice clean look that you see at each of the merging. Before we did some of this geometry studies, and we even continued to pursue some of these things throughout the construction phase and working together with the fabricator to sort of alleviate some of those conditions you see above, because this thing is a sphere, so it's not always so easy to have everything be 2D planar when you have circles and different planes. So in order to get those to join nicely, there a lot of care and attention was paid to developing that. And just to give the most basic understanding of how this framework is, you know, it is very complex at first, but in the end, it is still very much a dome. So to just kind of cover the basic behavior of these kinds of systems is you have a series of meridional forces that run vertically up and down the dome. And those are those red lines there. And then those are always in compression. It's like if you had an arch and you just kept rotating it around a circle. And then constraining that arch from bowing out as the gravity loads and the self weight of the structure is imposed, a series of hoop forces develop around the whole circumference of the system. And depending on where you're at throughout the height of the dome, those hoop stresses are either in tension or compression. So at the top, it's in compression where it's pushing down, and so it's coming in, and then at the base, those hoop stresses are in tension because it wants to splay out at the base. And so those hoop stresses are restraining it. And with everything being equal in sort of a perfect world, you can mathematically derive that area where that changes is about at the 52% marker or 52 degree marker from vertical. And so in our system here, it might be a little bit of an odd looking path, but you know, we do find that with red being the compression and the tension line. So as you go up and down vertically, you see that everything is primarily in compression. And then once you get beyond a certain threshold, you have that tension stresses that you have go around the ring and help restrain that structure. And with the top being primarily in compression and this being such a slender and elegant grid shell, you really have to be careful about the sensitivity of the structure to buckling, and not just buckling under the applied loads, but also you have to really be careful to manage the imperfections that might occur during the construction. If something starts to be built slightly out of tolerance, those can have really big knock-on effects on the structural design as a whole. So the way to manage about that is to constantly be analyzing your structure and be benchmarking and ensuring that you're not outside some normal bounds. So generally the simplest thing to think of is whatever your factor of safety is against your buckling loads. That's this kind of bottom axis on the chart here. So if you were at a value of 5, that would mean that your loads would need to be 5 times what they are in order to induce buckling. And if that were the case, you actually do start to see some amplifications in design stress that are on the order of about 25%. So the further you are away and to the right and the higher that factor of safety is, the better, because that amplification is very minor. But if you really are on a threshold and really close and really designing something to the absolute limit, there can be some really intense increases in stress, and that's something that we were continuously mindful of and designed against. And so we had to look at tens and hundreds of different possibilities that could occur, and these are just a few buckled shapes, but we had looked at them for all different conditions: wind, seismic. We looked at conditions where you had unbalanced sand at the top as it was so sensitive, and it really is quite a lot of analysis work to go through all these things. And so we even have developed some sort of custom scripts as we went along in order to generate through these and do all the design checks and manage these things and be able to run them overnight and be able to work effectively. And the other thing I just want to highlight about the region is seismically, it's more or less moderate. The Dubai municipality sort of imposes some higher limits that you have to design for, but in general, it's mostly wind governed. And we had done a high performance pressure irrigation wind model with RWI for this, because it is a very unique dome that has a center oculus that's open at the top, and there's all this area below with all the arches and the gateways that wind is able to travel through relatively freely. And so it's quite different than just a solid dome. And we did get a lot of benefit from doing this wind tunnel test. We actually found quite a dramatic drop in some of the pressures in relation to code pressures. And on the chart here, there's is just the general wind speeds of the region, and that red dot is what the DM has you target. So it's generally a little bit higher than what you have in the region. And so that was very important that we had this wind tunnel test so we can reduce some of those wind load demands. And the final part of the design I just want to touch on is all these connections. Well, ultimately, we were not the final connection designer for the project. That got awarded to the fabricator, who had their own engineers that executed that work, because it really, some of it is dependent on really how they want to build it. And so in this situation, we just did enough work to justify to ourselves that the frame elements that we were designing there wasn't going to be any hidden surprises as we got into the fabrication. They started to do some more of this rigorous analysis and find that all of a sudden everything needed to get so much thicker in these areas. So here are just a couple of snapshots of when Chimolai was first awarded, and they had put together several mock-ups of some of the different nodes and different ideas of how they wanted to approach it. So what we had done, we did a lot of modeling in place. We did a lot of mesh sensitivity studies and things of that nature. And you know, pretty much everything short of just specifying all the welds, but we really ran through a lot of the same checks that the fabricator's engineer ultimately wound up doing. And so we went completely top to down, top to bottom of the entire framework, and I identified each unique node and looked at sort of the controlling cases for each. And ultimately, in the end, this is the system we wound up with. We had 65 KSI steel, which is a S460 steel equivalent. A lot of that steel was coming from Europe, but there was also some from China. 20-inch in diameter all throughout, because we wanted to maintain a consistent diameter to help facilitate those connections, and also consistent look across the whole trellis. And the majority of it is in the 1/2 inch to inch thick range, but in some big high profile areas like the UAE entrance, they do get up to 2 inches for those big arches. But in the end, it was very lightweight, very elegant structure at only 15 PSF. So very well performing, efficient structure. And it wasn't just the framework that we paid a lot of detail to. We worked very closely with Tim and his team on just helping to define the fabric brackets themselves to attach to the steel members. And this was primarily done through using topology optimization. You know, we generally have an idea of what sort of optimum forms are, but in this kind of process, you start with a given design domain, what you saw in the beginning, and then at each step, you start to pull away material bit by bit where things are not really doing a whole lot for you. And you can either be doing that on a stiffness basis or a stress basis, and looking at different boundary conditions and the like. And so like on the bottom left, for instance, you see a situation where you're telling that you can only remove material on the outside. And by doing that, you start to see how fruit actually winds up being the shape that it is, because in nature, that is the most efficient shape that it wants to be. And so, you know, maybe for these 2 slides here, I think maybe you just want to walk through that.
Yeah, so what we're showing here, and this relates to the idea of what JJ was discussing, is topological optimization. And what that really means is you're removing all the material that you don't need, and you're just keeping the material where the structural load paths are. So the top left image is showing just a simple steel plate bracket that was originally proposed, and this is working with the fabricator, Tayo. And so we thought, hey, you know, this is pretty simple, but we can slim this down and we can make it a bit more elegant as well. So running it through the topological optimization process, where we anchor the ends where it will be welded to the steel pipe, and then introducing the stress forces from the tensioning bolts, which you see in the bottom right mock-up there. this started to reveal the optimal path where we could keep the structure and then remove any of the materials. So what we ended up doing was reducing the overall amount of material by about 45%, which, okay, it may seem not so much. So the baseline bracket on the left weighed about 2.5 kilos, and the one on the right, which was fully optimized, ended up weighing about 1.5 kilos. So if you spread that over the 17,000 brackets, then it starts to add up. So this was an interesting process, a small part of the overall trellis, but something that was quite interesting.
All right, thanks, Tim. So then now I'll get into the fabrication for a little bit before handing it off again. And when this fabrication process began, and because of the scheduling that the fabricator had to hit, there was a really aggressive push to be able to work fast and be able to work through a lot of different iterations and get answers to questions on things. So ultimately, I wound up going and being stationed in the fabricator's office, was Chimway, in the northeastern part of Venice there. It's actually about an hour and a half away. And as we said earlier, the full design contracting team was, general contracting team was Chimway and Riemann. That's a joint venture between these two Italian companies. I was there for probably a period of 4 to 5 months as they were in the thick of it, of doing all these different mock-ups and also putting everything together. So just a brief snapshot of Chimway. They've done some pretty high profile and complex projects throughout the world. So they really were a good fit for us for this to deliver this project. On the left, we have the Wasl in New York, and they also did work on the culture set, which you sort of see in the background there. And then on the right is the Panama Canal. So big, large-scale structures are not new for this organization. And even before they were awarded, there was actually quite a bit of attention where there was a pre-construction steel assist team that was also working with the design team to help us define things really early on too. So when we did finally get to that award phase, there wasn't going to be any big surprises. So there was a site mock-up that was done, and this was used to do many things like test different paint colors and look at different bracketing and different fabric joining and things of that nature, even different like steel connection approaches. So this really was used to define a lot of things for us early on. And then when Chimway came on, they also did a lot of their own mock-ups, and then some of these are just a couple images from the first workshop that we had with them. And they were almost like living shop drawings, where this was a mock-up, and a lot of this was to define a lot of the finishing that was going to occur in the final product, and in relation to the grinding of the welds and how that transitioning works out, how the seam shows up or how the seam's ground down, many different things. And just to give you an idea of how some of the finishes on these things look, on the left, there's seamless pipe where you don't have a seam because the pipe is made by being extruded through a die. And on the right, there is a seam in that member because it starts out as a flat plate and then it gets rolled up through the means of a mechanical press. So a lot of attention paid looking at different sort of situations. A lot of this, the seam pipe is something that Chimway manufactures themselves, but because so much workshop space was really being devoted to the development of the actual frame, in the end, it wound up just being more appropriate for many concerns, and especially aesthetically, to go with the seamless pipe. But the only issue with the seamless pipe is, and this was something a little bit interesting to us, I mean, when it got painted, and for us as structural designers, it looks like painted steel, and that's sort of what we expected. But that pitted look was not exactly the smooth kind of finish that you get with the bent plate on the right. So there was really a desire to have the finished look of the left, or the finished look of the right rather, but not have the seam of the right and be more like the left. So ultimately a epoxy was used, and I'll get into that a little bit later. So this just shows this giant press that they had where they actually make the pipe there. And then as we get into discussion about grinding some of the welds, it's important to make sure that you're careful about what sort of specification you're saying, because depending on where you're at, there's certain different meanings about what exactly is ground smooth filled. Now, ground smooth filled in newer versions is very clear about being a very clean and polished look, but in the 2010 version, at least, there was allowed to be a little bit of a lip, as much as like a 1/16 of an inch, 2 millimeters. So if it wanted to be ground smooth, then it needed to be a higher classification. So this is really stresses the importance of doing mock-ups, being very clear in the specifications, not just selecting certain AESS levels, but really paying attention and putting together a good set of documents to outline the expectations for how things want to look. And to get a little bit now on the mechanical side of the actual bending of the pipe, we have most of the bends on this project are really tight, and most of them are so tight that they can't be done through mechanical means, and they have to be done through induction bending. And I'll show those two processes in a minute. But the big takeaway from this is when you do bend a pipe, two really major things happen. One is in that upper right there, the pipe actually starts to get oval in manner as you bend it along the one plane, because it's getting squished. And you can set certain percentage degrees about what is acceptable, and we also didn't want to have it to be too much, not just aesthetically, but as these pipes meet together, it was really dependent on them being still circular when they matched up. So we had really tight tolerances of that, and it does have some minor structural impacts like changing the section properties, but not really too much. The big one for us is the wall thinning, is that when you do these really tight bends, the inside of the bends get really stretched because they need to make these really tight bends. So it's just something that we have to acknowledge and keep in our mind when we do design these elements, that there is going to be some section loss in certain parts of it's not necessarily loss, because actually the walls get thicker in the outside, the wall thing that occurs on the outside, it gets thicker on the inside as it's compressing, and then on the outside it needs to stretch. And there's also some crippling, but that's not really a big concern with the induction bending. If they go slow enough, you don't really get that waviness. It's actually pretty clean. And so again, this is just the ovality and how it can change some of those properties. So for the big arches, they were able to feed them in cold bending machines. They put in the whole arch, the biggest section that they could, and have it just come down and press it, and then they can get those pretty big radius. But then for the induction bending, that's actually a machine, and I'll have a quick video that shows this process where the pipe, and here you see it heated up. There's a coil on the outside of it, and it's electromagnetic, and it's heated up, and it heats the steel. And as it gets heated, it gets drawn through this process. There's a clamp on the end on a set of rollers, and it pulls it through and the gradual swoop to make whatever that bend is, and then immediately cools it, and that's why you see the steam there as it comes off. And after each one of those bends, it's quite a bit of work that gets done to those elements. And it's so much so that it actually changes some of the mechanical properties. And in order to revert back to it, these go into giant ovens for 8 to 10 hour heat treatments that help get it back to the properties where they used to be. And that was something that was very important for us, because they were doing structural work for us, and it wasn't just for conduit or something where it might not be necessary to do this. So I'll very quickly here to wrap up, just step through the workshop and kind of show you how they put each of these things together before they ship them off to Dubai. So here's the staging area. They had all the pipes, and then once they had the pipes and some of the bent ones, which they had got from other places, they had ground off the edges to do all the weld prep for each of them. Each ring was done in a series of 120 degrees. And that's why you see 3 different sort of zones there. And then they would fully weld them up with the complete joint penetration welds. Not necessarily where the site welds were going to be, but just to get them as one continuous ring. And then from there, they would cut off wherever they needed to for each of the different connections to adjacent rings. And then at that point in time, they would also have the jig to put in all the fabric brackets that you can see around there. And there you can see that full penetration weld up top there. And then once they got all that put together, they also had some splice plates that helped facilitate that connection. The splice plates did a few things for them. It gave them a clean surface to weld to. And the reason why they have those openings there, so all those conduits for all the different LEDs and other systems would be able to be fed through uninterrupted. So once what you see here, it's kind of in a giant fit up frame, which you'll see in the next photo. And they get everything geometrically right before then they make the full connections between the adjacent pieces. And then there you see an intended splice area that they're going to have for the different modules that they ship out. So this just gives a little bit of a scale of them, and then here's kind of a shot from above. They had like a small crane there one day in order to take a photo. So this would occupy quite an extreme amount of space in their shop, but it was really necessary to make sure all this geometrical stuff was correct. And then finally to finish, perhaps Tim, you want to talk about this one a little bit with the
Sure.
painting?
Yeah, so as JJ mentioned, one of the issues with the seamless pipe is the pitting. So what we wanted to do at the lower levels between, say, ground level and close to 15 to 20 meters, depending on where the rings are starting to connect up there, we wanted to create a smooth, almost glass-like finish. So in order to do that, this image is actually showing the filler and priming process to fill in all the pitting and make it smooth. So the end result for the lower 15 meters is a surface that is very, very smooth, and it's almost on par with an automotive finish. Not quite, but because we're dealing with heavy steel, it's a finish that you typically don't see on steel pipes of this size and magnitude.
Yeah, it's incredibly challenging too, being on a round surface. There was really a lot of effort spent into
A lot of
getting that look.
sanding.
A lot of sanding.
A lot of sanding.
And then so here we have our finished product, and then it got put on a boat and then shipped off down to Dubai. So initially I'd say maybe roughly about the first third of the trellis was fabricated in Italy itself proper. And then when they had sent these modules to go on, and then they started to get their site work up and going and working with their local fabricator, they did wind up fabricating the rest in Dubai, actually. So there's a little bit in each location. And I'll spend a few minutes here talking about the structural implications on the erection, and then I'll have Tim finish this up as he was the one on site, and also talk about the immersive experience. So really quickly, the final solution that was applied in order to erect the trellis was because of all the constraints that we have all these buildings around, we have a basement in the center, as I mentioned, there's also the tunnel. It was really tight, and it was really difficult to come up with ways to have cranes on the outside, have cranes on the inside. There wasn't a whole lot of area to put stuff. So ultimately, what was the best course of action for logistics and had a lot of structural benefits too, was that the first 2/3 of the trellis were erected in place. So you start to see these things stack up in the first 3 photos here. And then in the fourth one, you start to see these strand jacking towers come up around the perimeter. And these strand jacking towers also help serve as the frame that would support the first half, and then also help, there was scaffolding everywhere too, because they need to do all the site welding. And then in the center, they built the upper hat of the trellis. And over a period of about a day and a half, they lifted it up from the base and installed it on the top, and then maybe about a period of a month after, finished all the site welding around and to finalize that connection, and then released the strings. So just a quick snapshot of all the scaffolding. And again, here's that frame with the different strand jack towers, and in the center too. So everything was being very much in place. In some situations, you really have to be mindful of how things are going to be built. We design everything to be in finished condition, but we have to acknowledge the fact that there might be some intermediate steps in order to get there. But in this situation, everything was really sort of built in the final shape and place that it was going to be. The only thing that really sort of had some extra attention paid to it was that connection between the two, because there were some things like some cables in the center that kept it from splaying out as it lifted. And some of that is imparting loads onto the trellis that were not necessarily in the initial design. But because we knew those things going in the beginning, we had planned and given some considerations to that from the start. So it was not a major issue that we had to address. We just had to make sure all our assumptions were aligned with the fabricator engineer, Faith, who had done all this analysis work in order to justify their approach and make sure that all the working stresses and everything were acceptable. And finally here, just a snapshot of how that no connection occurred. There was actually a makeup piece that had to go in between in order to, because you needed to give space in order to lift it up. And then once they had everything in place, they would release each of the cables in the center, sort of in a way of like tightening a drum or detightening a drum head, where you go at each end, you release them and then go work your way around in a circle. And so you're kind of doing everything in an even balanced manner so you can get everything to line up nicely in the end.
Okay. So this image here is showing the future site of Expo before any of the ground has been broken. So just desert. And then in 2017, towards the end of the year, they started their enabling works. And what you're seeing here is, well, we can go back. What you're seeing here is enabling works. So some of the concrete blinding is starting for what JJ described before as our ring beam in the basement. And then as we start to get towards the end of 2017, you can start to see the columns that form part of the substructure for the trellis getting cast and erected. Again, here, this is showing, we can go back. This is showing the scale of the underground structures. So these ring beams are about 1.5 meters by 1.5 meters, and I believe about a height for these columns is about 6 to 7 meters. And then there's a bit of a pause while things started to take place above grade in preparation for the erection process. So what you're seeing here are the first elements starting to get erected. And so what actually happened is they erected every other column until they completed the ring, and then they infilled it with the columns in between. And once those were all erected, then it became a sturdy foundation for which they could start adding elements on top. And so what you're seeing here is many of the loose pieces, they're waiting aggregated assembly. And so what actually happened in a separate area from the site was these smaller pieces were assembled onto jigs into larger aggregates to ensure the precision and the fit. So they were all surveyed prior to being trucked over to the site. So this would be their chimalized laydown yard for storage and then pre-assembly. And so as we start to progress towards the end of 2018, you can see that the pieces are starting to grow on top of the first pieces here. So on the left, you can start to see some of the larger ring assemblies being stacked on top. And what's actually happening to the right, you're seeing temporary scaffolding that's holding up the initial columns. And then as those start to get connected and are free to stand on their own, those are removed. And on the left, a more lightweight K-trussing starts to be erected in order to maintain stability as we move upwards with the elements. Again, this is, you can go back a couple slides. Yeah. So again, here you start to see the aggregated assembly starting to grow on the left-hand side. And in parallel with all this temporary scaffolding, we're starting to see the king posts for where the strand jacks would eventually be assembled on the top. Go next. And so here on the left-hand portion of this image, we're starting to see the last elements of what we call ring one, which is the lower half, the lower 47 meters of the trellis. And so these king posts, they serve both as braces for the K-trussing, and they're also serving to do the strand jack lifting later on. And what's interesting, JJ touched on this a little bit, was because of all the activity, as you can see, there's numerous buildings going on. There's all sorts of construction activity happening all around. So the site started to get quite congested. And what you're seeing here in the middle, we have a tower crane that was erected in order to expedite the pre-assembly of these larger elements. So the loose pieces that we showed you from the laydown area earlier start to get aggregated in the middle of this picture into larger elements, which are then lifted into place with these crawler cranes that you see to the right of the image. This is actually an image taken from the main entryway that people will take into Wasl Trellis. And what you can see here is that the ring 1 is completed. And so these chevron elements mark the top of that. And then what we discussed earlier about the steel pipes and the various sizes, here you're seeing a gateway arch, which is a bit larger than normal, and this allows for vehicular pass-through as well. Again, this is another image, and you can see through the steel in the foreground all these aggregated elements that, you know, could end up being 15, 20 meters long, and these were all lifted into place with crawler cranes. So it was quite impressive when they started lifting these larger elements. So here, what we're starting to see is the assembly of the upper portion of the dome, which took place within the bounds of Wasl Trellis. So it was essentially erected in place, and then all we had to do was lift it vertically and complete the connection. So again, showing how congested it started to get. So the tower crane served a purpose to help expedite lifting the smaller pieces into place. And here we're coming in on closing up the ring 2. And you can see on the slings on the left here, we have one of the largest elements for ring 2, which is a chevron, which is about 10 meters long. So this is showing we're getting pretty close to completing the concentric ring. And so the path on the left, what they actually ended up doing was working their way outwards so that these crawler cranes, which were, you know, up to 10 stories tall, could eventually back out because they weren't able to lift over the ring 1, which you can see in the background. So it was a complicated process, but eventually we got there. And then this is showing the completed ring 1 or ring 2. And we've started to insert some of the fabric. Now, one of the interesting things about this image is, while it would have been ideal to put all the fabric in while this was on the ground, there was issues with uplift. So you can imagine if all the fabric was in place, this thing would want to blow away in the wind. So there was a limited amount of fabric that we could put in. And this is showing we're about halfway through the strand jacking process. So you can see all these strands that are hanging from the top of these king posts. And the image in the middle, second from the left, is actually the actual jack, which is surprisingly not that big. And the image on the right is showing the wires for scale. So relatively, it was a very light component that lifted this into place. And the image on the left is showing once we finally got it up to the right elevation, there's about a 500 millimeter portion that left unconnected. So there would be an infill piece that goes into there. So once these cleats were attached and the alignment was completed and surveyed, then we would insert the infill piece here. And then the middle image, second from the right, is showing the radial arrangement of the tension wires. So you can imagine if you just were pulling up on the edges of this dome, it would want to pancake and flatten out. So the interesting thing about this radial arrangement was it allowed the guys who were lifting it to introduce tension or release pressure in order to align the steel and keep it from flattening out. Again, this is showing the final spot when it's been completed and lifted into place. And we ended up leaving these radial tension wires in place until all the connections were completed. So all the infill pieces. And then once the infill pieces were welded and inspected, then we could remove the tension from this, and then the trellis start to stand on its own, and the king posts start to get disassembled. This is a video that Expo did during the strand jacking. Okay. So next we'll go over the fabric and some of the bespoke components that make up the immersive experience. And so just so everybody gets an understanding of how much infrastructure is actually within the steel tubes, we have speakers, we have video signals, we have low voltage lines, BMS, water, aviation lights. So it starts to become highly congested. So one of the key strategies here was determining the routes for everything to take. And the image on the right is actually showing how this stuff starts to come out. And then there's a sealing mechanism that was developed together with the contractor in order to keep the outside environment from penetrating into the steel tubes. So once they exit the steel tubes, there's an underground trench, and then from there, everything runs the circumference of the plaza and enters into the basement to their designated termination point. So starting with the fabric panels, the fabric is a PTFE fiberglass mesh, which is basically a Teflon coated fiberglass mesh. And one of the important things when we were searching out the materials is to find something that is non-combustible. So ultimately there were only a limited number of options in order to get the Class A rating. So this PTFE fiberglass mesh, which has an open area of about 20%, made the cut. And so this is made by St. Gobain in New Hampshire, USA, and it was fabricated and cut by Tayo in their factory in Shanghai, China. So this is showing some of the process that took place in the workshop. So what ends up happening is you get a roll that's several hundred meters long, and the rolls are about 3.8 meters in width. And so that gets delivered to the fabricator. From there, we have our designs for the template for each fabric panel, which are cut by CNC. And then following that process, we start to weld them together. So each panel is made up of 3 strips. You can see the image on the left there. And then they're heat welded together with a solid PTFE shear fill strip. And then what you see in the middle here, it's sort of shiny. There's a clear FEP tape on either side, which acts as the glue. And then one of the complications for welding these and getting this hem seam for the round parts is using a template to make these pie cuts to ensure that the edges aren't ragged and that it's a clean, uniform, crisp perimeter edge around each panel. And so after that process, this black strip here, which is an EPDM rope edge, is slotted through the void here. And this serves as an anchor for an aluminum extrusion that holds this, and in turn is used to tighten the fabric against the steel. So another interesting thing is that in the factory here, in order to prevent any kind of blemishes on the fabric, it's in a total clean room. So it's dust free, and it's quite interesting in how they clean everything before they weld. So it's almost like a hospital. So moving on here, this is after the panels have been fabricated, shipped to site, and then they're unrolled. And here you see part of the crew starting to assemble the aluminum rails, which you can see are these rounded shapes. And so there's straight parts, but they come in lengths of about 3 meters, just in order for ease of putting everything together. So once they have these aluminum extrusions attached to the fabric panel, then there's a specialized team of abseilers, and you can see in the middle image here, and just for scale how large some of these panels are. So there's a crew of a couple guys that are waiting up at the top, and then a crane lifts the fabric into place, and then they stretch it between all the tie-back brackets, and then it's tightened. It's a bit of an oversimplification, but the general process is it's lifted into place, and you have these guys scaling across the trellis, tightening it. And starting on the immersive experience, and this is a critical part of the trellis, and also, you know, in legacy mode. So one of the things that we had to develop was, how do we start to enclose these very expensive laser projectors from the elements? And being in Dubai, there's a lot of dust in the environment. It also gets very humid in the summer. So what you're seeing here are bespoke enclosures that were inspired by airplane nacelles that are fully conditioned and house the fan coil units. And there's 6 laser projectors within each of these enclosures, in addition to all the various video equipment and hardware and electrical panels. So just a quick breakdown of some of the materials and components involved in the fabrication of these. These are all aluminum. So it's an aluminum shell that's hydroformed. There's aluminum ribs. And the only steel component are the arms that cantilever off the trellis. But the interesting thing of this is also that each projector is pitched in a different orientation in order to correspond to where those video projectors are pointing to on the fabric. So another important, we can go back. Another important aspect of this is the glass on this. And so what we ended up using is a dual pane assembly of 99% clear specialty glass, which is typically used for cinemas. And then it has an anti-reflective coating on all 4 sides of the 2 panes. And then there's hydrophobic coating on the outside and the inside. So the outside is to shed any precipitation and dust, and the inside, in the off chance that there's any condensation, to shed that as well. And then the projectors themselves are actually situated on rack and pinion drives with these trays that are able to slide in and out of the actual enclosure for maintenance and installs. So moving towards the actual fabrication of these, you know, it was a task trying to find a fabricator who could build these, because it's never been done before. And so we ended up finding a company, a talented workshop called Kinetica, based out of Monterrey, Mexico, that was able to take these to the next level. And there was a lot of design engineering that happened with these in conjunction with the Kinetica team. So what you're looking at here is a jig assembly that they've created in order to align precision all the ribs that make up the structure of this enclosure. So once these are tack welded, and you can see a little bit to the right, it's moved to a rotisserie jig where they complete the full penetration welds of all the ribs. And then another interesting part of this was because the actual shell of these enclosures is doubly curved, and given the diameter of these, which is about 3.2 meters, it became difficult to find an existing company who could either stretch form or form these panels some other way. So Kinetica ended up building their own hydroform, and that's the image to the left there. So what actually happens is they feed in a flat piece of 16 gauge aluminum, and then they close the mold, and then they inject high pressure water. And then what results is the image in the top middle here, which is our perfectly formed panel that then gets sent to a CNC router, which cuts out the exact piece from what was hydroformed. And so the image to the right is showing after it's been cut, and there's 8 panels that make up the exterior skin. So what's happening here is they're starting to stitch together the aluminum panels. And then the image to the bottom left is showing one of the support arms that, again, we talk about the induction bending. So there was some of that process involved here as well. And within these tubes also, there's the video lines that eventually have to be fed through. And what we're showing here is the fabrication line within their factory. So there's a bunch of various components. So we have the rear frames, and this is all aluminum construction. We have the internal skin, which is aluminum being applied in the far left, as well as the insulation. And then also we're seeing the painting booths in the background. So this image on the left is showing a transport frame, which also doubled as the lifting cage for the erection on site. And so given the nature of the material and the paint job, which you can see on the right, which is actually a base coat of polyurethane followed by 5 layers of clear coat mixed with gold flake. So in order to protect that and protect all the finishing that had been done to these things, these transport cases were served double duty as they were shipped from Mexico to Dubai, and then also for the lifting. And then once it was bolted into place, then this frame was removed, and then you can sort of see these black conduits. Those are connections that would have to be made mid-lift to the bibs that were waiting inside the trellis. And then moving on to the speaker enclosures, these were built by Kinetica as well. So these house the speakers and the subwoofers, and these were designed in conjunction with acoustic consultants so that all the sound waves are projected towards the plaza. If we go to the next slide. So one of the interesting things about these is it's basically a 2-part design. The top half and the rear of the enclosure are acoustically opaque. And what we ended up using was ultra high performance concrete that was cast into the frame. And this helps reflect sound back towards the plaza. The bottom half and the front are what we call acoustically transparent. So we're utilizing a specialty fabric, which is 10 millimeters thick and dyed to match the trellis color. And this allows sound to pass through, but prevents a lot of the dust particulate from entering. And so this system was actually built with 13 millimeter steel plates for the ribs. And then these were anchored to the structure with steel pylons, which were wrapped in fiberglass covers. So what we're seeing here is the process of building the mold for which we would eventually cast the UHPC. So that's the image on the left. Again, there was some hydroforming that happened along with this as well. And then the image on the right is showing the rib structure with Nelson studs welded here. So this helps to anchor the ultra high performance concrete to the frame. So the image on the left is showing the steel pylon in its raw state. So the part that's sitting on the ground, this would be anchored to the trellis structure and all the necessary conduit routed through this element. And then the images in the middle are showing the fiberglass covers prior to painting, and the fiberglass covers enshrouding this pylon, and then the final state once it's installed, fully painted and finished. And one thing to note, which I'm going to touch on in the next slide, is in the image to the right, you'll see a rectangular cutout in the side of this enclosure, and that's for the maintenance guys to electronically operate the front part of this enclosure, which opens for maintenance. Go next. So this image on the left is showing the part that's actually movable. So this rotates about 100 degrees to allow for installs and maintenance. And the gray element here that we're looking at is actually formed from a flat piece of aluminum that is spun. So what basically happens is they apply this flat piece of aluminum, and then they apply a rounded bulb, slowly applying pressure to create this curved shape so that there's no joints. And what we're told is this is the largest spun aluminum pieces in North America. So this was an interesting process, and Connecticut ended up having to make a jig for the fabricator who actually spun these. And then within this lip skin, this rounded part, there's actually a magnetic lock system that keeps this closed and secured during the typical operation that you see. So that concludes. I mean, it was a fairly brief, I would say, somewhat high level overview. So hopefully that was enough to convey some of the bigger ideas that we had and all the work that we had to put into this.
Thank you guys. I think it was a great presentation, a lot of very interesting images that definitely show kind of a behind the scenes view of how these big things get made. There's only one question, so I know it's a little after 6, but I'm gonna go ahead and do it. I believe it's for JJ. From Bubisino Hartono, the question is, did you have the top ring beam pre-stressed?
No, we did not. It actually, it's, you can maybe tell in some of the earlier images and photos, but it actually comes back in on itself a little bit at the base, so that it's more of a compression ring than being a tension ring at the base. So it's almost dominantly compression at the base there. So there was no need to pre-stress it with it being concrete. But that's a good question.
All right, so I think that's it for questions. So once again, on behalf of the CTBUH Future Leaders Committee, we'd like to thank our speakers for taking the time to share this great presentation with us.
Yep. And if anybody has any additional things, please feel free to reach out to me. Always happy to chat.